We're running low on time. I'm Mason.
I'm Nikki.
This is Lab10 388.
Semiconductor sources with Raphael.
The first part of this experiment is to look at an LD under the microscope to find the dimensions of the cavity and understand where the light comes from. We found the dimensions to be 1.5 millimeters here and 2 millimeters here. When we flip the cavity on its side, we can turn on the laser diode and see that the light emission comes from this very small area right here. This area is only 1 by 3 micrometers. This is the LED under the microscope with the blue light turned on. As you can see here, this is the emission area for the light, and we found its dimensions to be 1 by 1 millimeter, and that's the same for the other two emission areas as well.
The purpose of this part is to examine the relationship between the input voltage and the output power of the LED. So to do that, we changed the voltage and recorded the power. And then we plotted it, and as you can see here, it follows a pretty linear pattern until it maxes out. We then repeated the experiment but with a laser diode and got this result. And as you can see, it matches pretty closely to the expected result with a very sharp incline. For the divergence bench, we rotated the source by a certain angle, and we recorded the output voltage peak to peak per the angle and plotted them. As you can see by our result graphs, the divergences of these sources vary wildly. For instance, the LED, with its incoherent light, has a very large divergence, and its peak is wide. And the divergence of the horizontal axes and vertical axes of the laser diode are much smaller, as the light is coherent and diverges much faster.
Here we use the radiance bench to understand the differences between the radiance of the LD and the LED. To do this, we look at the power output of each one with no aperture, with a small pinhole, and with a polarizer. From our results, we could calculate the relative radiance of the LD versus the LED to be 16 times greater, and the polarization ratio of the LD to be much, much greater than the polarization ratio of the LED.
For experiment 3, we will measure the spectrum of the 3 colors of the LED. We will use the software to measure the peak wavelength and the peak intensity and measure the full width half max. And when we collected our data, these were our results. And as you can see, for the green and red LEDs, the full width half max is a bit out of the expected range. And this error would be due to limitations in our software.
When we begin, we are below the laser threshold as seen on this oscilloscope. As we continue to move, we see a bunch of peaks and approach the lasing threshold. If we continue to increase the current, we are now in the lasing region. Continuing to increase the current further will create a mode jump, and we found the distance between these two modes to be 0.382 nanometers, which is within the 0.3 nanometer range expected.
We found the peak wavelength to be 647 nanometers and the peak bandwidth to be 0.041 nanometers. This is much greater than the 0.0001 nanometers due to an imperfect system.